Consider the graph of the function y is equal to f of x with domain D, the subset of real numbers. It is clear that the value of the function f at a point A is the maximum. That is, the value of the function at any other point to the left or right of A is less than f of A. Mathematically, a function f is said to have a maximum value at a point A in its domain if the value of the function at that point is greater than or equal to the value of the function at any other point in its domain. The number f of A is called the maximum value of f in D, and point A is called the point of maximum value of f in D. Now take a look at this graph. What do you observe? Yes, you got it right. In this case, the value of the function f at point A is the least. That is, the value of the function at any other point to the left or right of A is greater than f of A. Mathematically, a function f is said to have a minimum value at a point A in its domain if the value of the function at that point is less than or equal to the value of the function at any other point in its domain. The number f of A is called the minimum value of f in D, and point A is called the point of minimum value of f in D. If a function f has either the maximum value or the minimum value at a point A in its domain, then f is said to have an extreme value at that point. In such cases, the number f of A is called an extreme value of f in D, and point A is called an extreme point. Consider the function f of x is equal to 2x squared for all x belonging to the set of real numbers. Let us find the maximum and minimum values of this function in the domain R. The graph of the given function can be drawn as shown. Now, observe the graph carefully. The value of the function f at the point 0 is 0, and f of x is always greater than or equal to 0 for all real values of x. Therefore, the minimum value of the function is 0, and the point of minimum value of f is x is equal to 0. It may also be observed that there is no maximum value for this function, since the value of the function increases as x increases from 0, and also the value of the function increases as x decreases from 0. However, if we restrict the domain of function f to some closed interval, then its maximum value also exists. Let's verify this. Suppose the domain of function f is restricted to closed interval -2, 1. Then, the maximum value of the function is 8, which is at x is equal to -2. Let us consider another example. Let f of x is equal to modulus x plus 2 be a function defined for all x belonging to the set of real numbers. Let us find the maximum and minimum values, if any, of this function. The graph of the given function can be drawn as shown. Observe that the value of function f at x is equal to -2 is 0. Also observe that for all real values of x, the value of the function is always greater than or equal to 0. Therefore, the The function f has a minimum value of 0, and the point of minimum value of f is -2. Also observe that the function f has no maximum value in the set of real numbers, and hence no point of maximum value in the set of real numbers. However, if we restrict the domain of function f to some closed interval, then its maximum value also exists. For example, let us restrict the domain of the function f to closed interval -3, 1. In this case, the maximum value of the function is 3, which is at x is equal to 1. If you notice, you will observe that the function is not differentiable at x is equal to -2. This shows that a function has an extreme value at a point even if it is not differentiable at that point. In both the examples discussed, we saw that if we restrict the domain of the function to some closed interval, then the maximum and the minimum values of the functions exist. This discussion leads us to a result which states that every increasing or decreasing function assumes its maximum or minimum value at the endpoints of the domain of definition of the function. More generally, it can be stated that every continuous function on a closed interval has a maximum and a minimum value. Now, let's proceed further and learn about local maxima and local minima of a function. Take a look at the figure here. Observe that the curve of the function is increasing from point O to P, Q to R, and S to T, whereas it is decreasing from P to Q, R to S, and T to U. The points at which the nature of the function is changing from increasing to decreasing or from decreasing to increasing, that is, points P, Q, R, S, and T, are known as the turning points or stationary points of the given function. Also, if you observe the graph carefully, you will notice that the function has minimum values in some neighborhood of points Q and S, and has maximum values in some neighborhood of points P, R, and T. The points P, R, and T are called the points of local maximum, and the values at these points, that is, the y-coordinates of points P, R, and T, are the local maximum values of f of x at these points. Similarly, the points Q and S are called the points of local minimum, and the values at these points, that is, the y-coordinates of points Q and S, are called the local minimum values of f of x. The local maximum value and the local minimum value of a function are referred to as the local maxima and the local minima, respectively, of that function. Let us now define local maxima and local minima mathematically. Let f be a real valued function and let c be any point in the domain D of f. Then, C is called a point of local maxima if there is an h greater than 0, such that f at C is greater than or equal to f at x for all x in open interval c minus h, comma, c plus h. The value f of c is called the local maximum value of f. Also, c is called a point of local minima if there is an h greater than 0, such that f at c is less than or equal to f at x. For all x in open interval c minus h, comma, c plus h. The value f of c is called the local minimum value of f. Let us now understand the concept of local maxima and local minima graphically. Let the point of local maximum value of f be x is equal to a. Then the graph of the function f around a is as shown. Here function f is increasing in the open interval a minus h, comma, a, and is decreasing in the open interval a, comma, a plus h, where h is a small positive number. We have the derivative of the function at a is equal to 0. Now, let x is equal to a be the point of local minimum value of f. Then the graph of the function f around a is as shown. In this case, f is decreasing in the open interval a minus h, comma, a, and is increasing in the open interval a, comma, a plus h, where h is a small positive number. This means that the derivative of f towards the left of a is less than 0, and the derivative of f towards the right of a is greater than 0. Therefore, the derivative of f at point a is equal to 0. In view of the discussion, we can state a theorem. Let f be a real valued function defined on an open interval I. Suppose point A is any arbitrary point in I. If f has a local maxima or a local minima at the point x is equal to a, then either f dash a is equal to 0 or f is not differentiable at a. The proof of this theorem is beyond the scope of this lesson. However, remember that the converse of this theorem need not be true. That is, a point at which the derivative vanishes need not be the point of local maxima or local minima.